Okay, good day to all. Our topic is about construction estimate. As much as I wanted to share my knowledge, like a full course in this field, a day or three is not enough discussing all the details. So for a short of span of time, I decided just to show an overview or like basics on how it's done using MS Excel. First of all, construction estimate is the process of calculating all the required costs for a construction project, including direct costs of materials and worker wages, equipments, and the indirect costs, which are added factors to anticipate unwanted price changes, weather effects, and other instances that delays the project. The purpose of an estimate is to provide a reasonable idea of the cost and also an essential requirement when asking permit to construct. For this certain subject, I'll be discussing topics on formatting tips, DQC or quantity takeoff, bill of materials or BOM, and bill of quantity or the BOQ. To start with creating your own format, let's see first some samples of DQC, BOM, or BOQ. Shown already here are example 1 and 2 of DQC formats. Both are prepared from MS Excel, but example 1 is already in PDF file, which is ready to print. As you can see, the presentation of data is different. Example 2 is in table form, while example 1 is in manual mode, but still uses MS Excel to input data. Creation of your own format is your discretion. It depends if you feel example 1 is easier than example 2. Our concern here is which is more organized for you so that there would be no problem when you're linking your data to the bill of materials. Example 3 and 4 now is the bill of materials, which summarizes your computed quantity from quantity takeoff or DQC. It's more on list of materials with corresponding price, which leads to total cost as per item. Example 5 and 6 shows us different format of BOQ but same concept presenting the total material cost, labor cost, and indirect cost. Now, to start with your own DQC format, we can use the example as basis. As you open MS Excel application, try to resize your column cells to more slender with like 5. BOM starts with the project name, location, and owner. Let's just try to copy the format and leave blank the data. However, we're going to insert simple formula for the summation of costs. For the BOQ, it's like BOM, but there are additional details we need to insert like material cost, project duration, name of owner, and simple description of the project. Moving on, if your format is already done and complete, then grab the reference plan. You're ready to analyze quantities. DQC, or the detailed quantity computation, is the first step before we proceed to bill of materials. It is also sometimes called as quantity takeoff. The quantities we compute here shall be the data we're going to use for the BOM. The difference is that DQC helps us determine the quantity of materials to be ordered and the quantity of each construction item. Whereas BOM will tell us how much it will cost. It is where the price and costing is involved. This DQC is one of the critical part in estimating. It is where various formula will be put to use. Although it's all basic like area, length, and volume, I encourage you to have patience because DQC is really time consuming, but it is important. It is inevitable that you might encounter several particulars and sub-particulars of each item, especially for buildings. There are many items to consider versus horizontal structures like pavements and flood controls. Since our example is a bungalow building, we start our computation with earthworks. DQC for earthworks include structure excavation, structure backfill, gravel bedding, regular fill, and soil poisoning. We base our computation as shown in the structural plan, specifically at the foundation plan and cross-section details of footings, columns, ground floor slab, and grade beams. For the structure excavation, the yellow shaded part is what we will compute and use as an input. We remove or dig the material for the placement of foundation and substructures like wall footings and grade beam. In MS Excel, we organize our input data shown. For example, for the column footings, we manually count the number of units as per foundation plan and derive the volume by multiplying the area of footing to the depth of excavation, likewise with the wall footing. For the grade beam, we insert additional 0.05 meters allowance both sides, meaning a total of 0.1 meters excavation width. This is to give space for the installation of forms in preparation for concrete pouring. For the structural backfill, we just deduct the part of structure from the excavated part and consider only the spaces needed to be filled for the purpose of stability. This is what it looks like in our spreadsheet. It is the same as the excavation format, but we deduct the data of the structure. For example, the footing dimension of column is 1 by 1 and the column structure is 0.25 by 0.3. We subtract the area of the footing from the area of the column. And to derive the volume, we multiply the area to the depth of backfill, 1.20 meters. And then that's how we come up with the volume, with the value 21.09 cubic meters. Next item, the gravel bedding, is a layer of aggregate spreading across the bottom for the purpose of leveling the ground before concrete pouring and to avoid direct contact of the rebars to the soil earth. Again, to compute for the needed volume of aggregates, we maintain the area we derive from the excavation, but the thickness shall change to 0.1 meter. The width of the grade beam shall be 0.17 meters as per plan, and we also include the slab area. It is noted here area from CAD, meaning the data for computation is already provided and ready to be used. After computing the unit volume of the particulars, we now all add them all so we could derive the total volume of 132.08 cubic meters. For the regular fill, as per plan, we consider elevating the structure a bit higher at desired level than the natural ground level or NGL. As shown, we have distance of 400 mm from NGL to FFL or finished floor line. We only consider 300 mm since the slab is 4 inches thick or 100 mm thick. Sample format computation is as shown. We derive the irregular area from CAD multiplied by the uniform 0.3 meters depth till we derive a total volume of 31.31 cubic meters. Soil poisoning, it is considered as the control measure against unwanted termites. Although this is not shown in the plan, as estimators, we consider the preservation and protection of structures. So we consider here the slab area plus 1 meter allowance all through the perimeter. Once we have computed the area, we compute how many liters to order from the market, taking note for this particular product. 4 liters is equivalent to 40 square meters. 40 square meters is the productivity of one product like this, and one product is 4 liters. Say 4 divided by 40 is 0.1 liters per square meter. Then we multiplied that to the derived area. Now we get 21 liters to order. For concrete works, we still refer our estimate as per structural plan, mainly on the foundation plan, details, and cross-sections. Concrete works involve calculation of volume of concrete, then estimating the number of Portland cement, sand or S1, gravel or G1, and then the number of rebars needed, including the number 16 GI tie bars. Included items here are the following: reinforced concrete isolated footing, column, CHP wall footing, grade beam, roof beam, lintel beam, ground floor slab, reinforced concrete countertop. Well, estimate of concrete works becomes complex for multi-story projects. Some companies still use MS Excel, but others refrain. Instead, they use other applications for their own application format. However, for manageable small projects like this, MS Excel is still powerful and very convenient to use because you have the freedom to insert your own formula and create your own format in which you are more comfortable. My apologies, I might not discuss all the detailed quantity computation of all items. I am just giving an overview so at least you will have an idea how detailed quantity computation looks like. An hour or 3 is not enough to tackle all of it. I would like to suggest there would be separate seminar for this. Anyway, I have prepared slides for some items. Let's continue with the reinforced concrete isolated footing. Reinforced concrete isolated footing, as shown, we have 19 units with a length and width of 1 meter and thickness of 0.25 meter. From this data, we'll arrive with the volume of 4.75 cubic meters. To get the number of bags of cement, since RC footing is Class A with compressive strength of minimum 25 MPa, we multiply the volume 14.7 by the factor 9.94. For S1 and G1, we multiply the volume by 0.5 and 1.0 respectively. Waste factor of 1.10 is also included to anticipate if ever there will be inadequacy in the actual construction. Computation of rebar footings. As shown from the plan, we have 7 pieces of 20 mm diameter RSB both ways. Note that the RSB have a steel strength of 415 MPa or say G60. The minimum clear cover of the structure exposed to earth is 75 mm from bottom and 50 mm for both sides and the top. Computing the length of one footing cut bar is equal to 1 minus the total of 2 times half diameter of RSB, which is now 10 mm. 20 divided by 2 is 10 mm, plus clear cover of 0.075 meter, and then 2 times the thickness of the slab, 0.25 meter, minus the top and bottom clear cover, which is 0.05 and 0.075 meters respectively, minus half diameter of RSB, which is 10. This will be equivalent to 1.146 meters. Now, to determine the number of rebars to be ordered, we choose the available commercial length to be ordered, which ranges from 6 meters, 7.5 meters, 9 meters, 10.5 meters, and 12 meters. For this instance, we select the 6 meters commercial length. So, for each 6 meters, we have 5 pieces containing the computed unit length of 1.146. That is 6 divided by 1.146. We have 5 pieces containing the computed unit length. But how many total required number of pieces do we need? For the longitudinal bars or along x-axis, we have 7. And the number of footing is 19. So, 7 pieces times 19 footings equals 133 pieces. We can now determine the number of pieces to order by dividing the total required 133 pieces to available pieces per 6 meters, which is 5. Then, we'll arrive to the equivalent of 26.6 or say 27 pieces. Since transverse and longitudinal are alike, we can multiply this quantity to 2. Therefore, 27 pieces times 2 equals 54. Then 54 is the number of pieces of 20 mm diameter RSB we can order. Computation of GI tie wire starts with computing the number of joints, 7 times 7 times 19 footings. Note that per tie, we have 0.30 meters minimum length. Total length then is 0.3 meters times 0.3 meters times 931 pieces equals to 79.30 meters. And since 1 kilogram of tie wire is 53 meters, we divide 279.30 meters to 53 meters, which is now equal to 5.27 kilograms or say order 6 kilograms of tie wire. This is how it looks like when you input your data in Excel. Make sure if you make your own format, make it neat, simple, understandable, and easy to use for your next estimate project. Moving on with our next topic, the bill of materials is part of construction estimate where we indicate price and costing of the materials and quantity we have computed from the DQC. Bill of materials or BOM is a structured list identifying all materials and components required in our project. Shown here are two examples of BOM of two different projects. We can simply differentiate the appearance and the presentation of data, but as we can see, they have the same concept because what's important is the list of materials needed and the costing. Most BOMs include the following elements like project name, description, quantity, cost, and the unit of measure. This includes components and parts, but it does not include labor. The Bill of Quantities or BOQ is a document that contains information on the quantity of materials, labor, and their cost in a construction project, while BOM is related to the list of inventory of raw materials, parts, and components. BOQ is like BOM, but it involves costing of labor too, and other indirect costs now. The basic elements are project name, owner, project cost, number of calendar days, description, table of estimate with summed up materials, labor, direct and indirect costings. Shown are two examples of presentation of BOQ. We notice here they differ in orientation and format, but the same concept in arriving the important details such as material cost, labor, and equipment cost plus indirect cost. Example 1 is a sample format provided by a company, while example 2 is a format I have created which includes same details indicated from example 1, but I added in the heading the perspective, projected duration, total material cost, project cost, and short description containing also the length and width of the building. One thing I make sure is that it would be easy for the owner or contractor to analyze the BOQ as well with the building official who would be approving the permit. If you're having a hard time coping up with or coming up with the format of your own, you might want to consider getting a template for your convenience. There are many formats in the internet for your basis. Some are free. I understand I understand starting a form on your own can be challenging or tricky, but using a template I allow you to directly fill in the sheets with all the data you've gathered. This way, instead of drafting out the document structure on your own, you can now search for a template that matches your bill of material or BOQ taste or type. This saves you a lot of time and effort. However, it is more commendable if you create your own in the long run. You can have your own discretion of style, formula, and presentation of data. So that ends our short free session for today. I hope you all learned something. Thank you for listening and good day.